Today we're going to talk about the derivatives of log and exponential functions, and we'll talk a little bit about logarithmic differentiation. So let's start off with the function y equals a to some power. And we'd like to know what the derivative is equal to. Well, what we can do in this case is take the log of both sides. Then, if we do that, we can use the property of logs that says we can make this exponent a coefficient. So we're going to write this as ln y equals x times the ln of a. Now we can take a derivative. Now on the right side, the derivative is just going to be ln of a because that's a constant. On the left, we know that the derivative of the natural log is 1 over y, and this is implicit differentiation, so we've got to multiply by the derivative of y. Then if we multiply both sides by y, we get that dy dx is equal to ln a times y, which means that dy dx is equal to y is a to the x times ln of a. So for example, if we wanted to find the derivative of y equals 3 to the x, the derivative is 3 to the x times the ln of 3. Now let's say that it wasn't just 3 to the x. Let's say it was 3 to the x squared. Now we'd have to use the chain rule. The derivative would be 3 to the x squared times ln 3, but then times the derivative of the exponent, which is 2x. So that was the derivative of some exponential functions. What if we wanted to find the derivative of a log function base a? Well, before we find the derivative, I'm going to rewrite this as an exponential function. This is a to the y is equal to x. And then here, if we take the natural log of both sides, ln a to the y is equal to ln x. We can rewrite this again, bringing that exponent to the front here, which means that y is 1 over ln a times ln x. So we can take this derivative, that's dy dx, is equal to 1 over ln a is just a constant, so that's going to stay the same. And we know the derivative of ln x is 1 over x. So the derivative of log base a of x is 1 over x ln a. So for example, if we wanted to find the derivative of y equals log base 3 of x, that would be 1 over x ln 3. But if instead this was y equals log base 3 of x squared, then y prime would be 1 over x squared ln 3 times the derivative of x squared, which is 2x. We can simplify a little bit and be left with 2 over x ln 3. So just a quick comment about log differentiation. That's what we were using when we take the log of both sides in order to help us find the derivative. That's called log differentiation. And there are several places that you might use that. One example would be, let's say you had y equals x to the x. Now the power rule doesn't apply because the power is a variable, and the rule we just learned about exponential functions doesn't apply because the base is a variable. So when we get to something like this, it's very helpful to take the natural log of both sides, because then we can use that property that allows us to bring this exponent to the front here. Now we can take the derivative of both sides. This is 1 over y dy dx. The right side we have to use the product rule. So we get 1 over y dy dx is equal to 1 plus ln x. And then if we multiply both sides by y, we get dy dx is equal to which is 1 plus ln x times x to the x. And here is our summary. We learned a few rules about the derivatives of exponential and log functions. And the derivative of a to the u would be a to the u ln a times the derivative of u. That's our chain rule. Then we learned about the derivatives of logs. So we have log base a of x. That derivative will be 1 over x ln a. But if we had log base a of u, where u is some function of x, that's now 1 over u ln a, again times the derivative of u. And last we learned about log differentiation, which allows us to use the rules of logarithms to find derivatives. And that involves, like our example was x to the x, taking the natural log of both sides to use those properties before we take a derivative.